Good morning, ladies and gentlemen, and I want to thank you for giving me the honor to talk to your association's conference today. I first would like to thank the players as the presenters of yesterday, and especially David, who gave quite an inspiring presentation to me. I'm also a family man, and I must say that was really nice. Thank you very much. You don't know me as a person, and I want to quickly introduce myself. I'm a chemical engineer by profession, and I started my career after my PhD at Hoechst in Frankfurt. At that time, Hoechst was one of the three big chemical companies of the world. BASF, Hoechst, and Bayer were the three biggest ones in the world when I started. And I started in process development and was involved in the plastics business. I didn't have any idea about pine chemicals. At that time, Hoechst was selling their polyethylene business. BASF, Shell, and Hoechst merged together to Elenac. And the head of that unit was at that time a person called Rolf Richter. And I learned that Michael Klamm, who is now at Symrise, was also at Elenac at that time, coming from the BASF side. We didn't meet, but that was the first touching point with pine chemicals, kind of. I moved on and became the plant manager of a pilot production. And then a funny thing happened. I changed 4 legal entities sitting at one desk. That was really a crazy time, like buying, selling, and everything. I was sitting at one desk, and it was a member at 4 legal entities. I ended up being a member at Siemens. 800 engineers were given to, or were sold to Siemens. I left Siemens rather soon and went to Clariant. And here I had another encounter with pine chemicals. I went into the global engineering department of Clariant. And one of the subsidiaries of Clariant was at that time Abieta Chemicals. Abieta Chemicals was later sold to private equity, of course, and then later to Arizona Chemicals, ending up at Kraton, of course. And when I had a meeting some time ago with Roy Harrison of Kraton and Thorsten Schmidt, we realized that Thorsten and I have been at Hoechst as well. So that was my first encounter. Later, I became a professor of chemical engineering at the University of Applied Sciences in Berlin. And this is where our story starts. 11 years ago, I became consultant to a company called Fibreboard. And you see, Fibreboard is a producer of laminate flooring as well as medium density fiberboard. They process around 1 million tons of wood dry matter per year. And I'm the external process development department, one can say. And even though I'm not a member of the company, I have my office there. So it's quite an interesting situation. I'm working for this company. As you see here, that's the site in Bayreuth, 1 hour south of Berlin. You see on the left-hand side, the MDF factory producing the medium density fiberboard, and on the right-hand side, the white buildings, that's the laminate flooring system. You know, possibly these floor products where with a tongue and groove system, you click together these sheets and then cover your floor. Together, this is the largest integrated MDF and laminate flooring site in the world. Maybe as a matter of scale, you see at the bottom 800 meters width and then 500 meters length. So that's quite a bit. And on the left-hand side, in the middle, that white building, that's the chip storage. So that's essentially one soccer pitch filled with wood chips, and that is lasting maybe for 3 or 4 days. So you have an idea of the order of magnitude. It's a bit smaller than a pulp mill. Capacity-wise, size-wise, it's even bigger. This is just another impression, so it's industrial scale operation. You see here a photo of the stack with the online VOC measurement. VOCs are volatile organic components. And this is where I started to get involved with pine chemicals. As you can see in this flow chart, the process, just a very quick introduction on that one. 400,000 tons of wood dry matter are being processed, debarked, sieved, washed, and then pre-steamed, being heated to 100 degrees centigrade. And this is actually very similar to chemical thermomechanical pulping in the pulp industry. They're then fed into a digestion unit where they're being digested at 170 degrees centigrade, 9 bars. In pulp and paper, would be like 130, 140 degrees centigrade. So far, very similar. Then comes a refiner, that's a rotor stator mill, 2 discs rotating about that size in diameter. And then this drive has 10 megawatt. I mean, 10 megawatt is a motor from here to the end of the stage, and we use a 500 kilowatt pony motor in order to start up the big one. So that's quite a bit. And that alone makes 10 tons of steam per hour dissipating the electrical input. That's quite big. Now comes the difference to pulp and paper. In pulp and paper, the steam and the fibers are being separated. And then the steam comes out anyway, including the turpentine. So these guys need to take care of it. We don't, or we didn't have to until recently. The process continues. There's quite a remarkable thing. Those 50 tons of wood, dry matter, 20 tons of steam, 40 tons of water go through a pipe of that diameter, 150 millimeters, with a speed of 200 meters per second, or like 750 kilometers per hour. That's really remarkable. And then injected into a dryer of that diameter, 50 meters long, 50 meters tall, and then comes a cyclone separator that separates the fibers from the drying air, giving 1 million cubic meters of air that is coming out, and the fibers are then being processed. They are pressed in a continuous press under pressure and temperature to form the MDF feed. Out comes a gas stream of 1 million cubic meters per hour. That would be some 600,000 cubic feet per minute. And there's wet scrubbing, but the wet scrubbing only gets out the small molecules, formaldehyde, acetaldehyde, formic acid, acetic acid, methanol, essentially. But there's something in there that cannot be taken out. Thermodynamically, you cannot dissolve terpenes in water, and here's where the story begins. We know that you can take them out by adsorption, as Kim was telling us, of course, but you cannot dissolve it in water. So we had the problem because emission values went down. You see here the values of like 200 milligrams per cubic meters of VOCs that we had. The new values that are allowed by the European Union are 100. So that was really threatening the plant. So we had to solve the problem and had to get them out 1,600 tons per year of VOCs. Now, the solution in the end led to this. We came up with a new route to produce turpentine. You know, of course, gum turpentine, wood turpentine, even though they're suffering a bit, crude sulfur turpentine. And this is MDF turpentine. This is from my carry-on luggage. I had it in my toiletry bag and declared it as perfume. If that were to be CFC, you would be running away. But you don't with this one. And it's really nice. So that's gum-like turpentine that we talk about. And then the next question is, how does that work? What we essentially do is upstream from the place where we add process chemicals, glue and other stuff, upstream, where the wood has only seen steam, nothing else. We take out a certain amount of steam at a certain place, which is quite anti-intuitive, and we can calculate the amount of steam being necessary. That's a fact, a matter of process design, but essentially thermodynamics. Depending on the amount of turpentine being present in the turpentine composition, I can calculate the amount of steam that has to be taken out. What we then do at the moment is we incinerate it, sorry to say, in order to solve the problem. And you see the solution on the left-hand side, the concentration goes down to 50 milligrams per cubic meters, 50 parts per million, so well below the emission value of 100. Problem solved. So that was already quite exciting. Then we realized, oh, wait a minute, there might be a value to that thing in there, those so-called terpenes. That's when I got involved with your industry. 3 years ago, I had no idea what rosin and turpentine are. I had no idea at all. And then we realized, oh wait, we could possibly condense it and then sell it as a product. And obviously, we shifted from the left-hand side to the right-hand side, and we can produce, and we will produce 150 kilograms per hour or 1,200 tons per year. Now, how does it look like? This is just a few impressions of the pilot unit we're using, as well as the incineration line. Currently, it's incinerated as a state. And here's a quick summary. First summary, the emission reduction is an industrial operation. It works very fine. Low investment, low operating costs. We even make use of like 1.8 megawatts, the heating value. So it's even a plus for the power station. No authority approval. That's a quick solution within a couple of months. So the industry is quite happy. Turpentine, we did the detail engineering already. The design is done. Procurement is underway. The plant will start production in next summer with 1,200 tons per year. That's the German summer, so that's July. We have authority approval started. REACH certification is granted already, so we can export any moment. We have heat recovery. So the OPEX, the operational expenditure, is essentially close to zero. And there's very fast amortization because the investment is not that high. Unfortunately, we're using Pinus sylvestris, Scots pine. And as a result of that, we have some 48% of alpha-pinene, 3% beta, 35% delta-3 carine. That's the way it is if you use Scots pine. There's no choice about that. And we produce in pilot scale, we can produce like 50, or at least provide 50 kilograms per hour. So barrel-wise or IBC-wise, we of course deal with samples, but we cannot really produce. And that's what you see here. On the next slide, you see a book. It's called Die Gewinnung des Harzes der Kiefer, the production of oleoresin from pine. In the former East Germany, German Democratic Republic, there was extensive tree tapping until 1989. When the wall came down, then immediately stopped because of labor cost. So it stopped immediately. But they were, of course, investigating that thoroughly and actually sent that book to Alejandro Cunningham because they have described extensive tree tapping techniques there and also how to stimulate the tree. Quite interesting. We source our pine from the former East Germany as well as from the Polish National Forest. And therefore, we have, of course, a very similar composition. You see here, this composition is very similar to what we found earlier on and what I reported. So the message is the process does not change the composition. Our turpentine is essentially the same as the former East German gum turpentine, unfortunately made from Pinus sylvestris. But we can change that. The next slide shows you our emission values. They're not really important to you. You see they're high on the left-hand side. We start our method. They are low after that. But what you can see is it's a stable process. It's a stable process in industrial operation. That's the message. And once we have a line of steam going from A to B, which is the power station, it's very obvious that if that runs so stable, we can easily take that steam and instead of incinerating it, condense it, subcool it, decant it. And the rest is very similar to CST recovery. Once you know where to tap the plant and how much steam to take out, the rest is normal chemical engineering stuff. That's not a problem at all. So the benefits are obviously, first of all, for us, we meet the EU regulations. If you build a new plant in the United States, you would not go for maximum achievable control techniques, which is buying a regenerative thermal oxidation. That's very expensive, millions of dollars of natural gas being fired to operate that. But you can go for BACT, and indeed, there are companies who are considering that at the moment. So operating costs, millions of dollars can just be avoided. And then, of course, our subject here is revenue creation by turpentine production, and you can actually do both, of course. I want to mention there's no influence on product performance, which is, of course, important because we don't sell turpentine There's only a side effect. We sell medium density fiberboard, of course. So the problem is, or the product is not involved at all. Low investment costs and almost no OPEX. That gives rise to the question, where does the product go? And this is something that you know, of course. This is the CST route, the gum turpentine route going to the CST distillers. Many of them are around here, of course. And there's also distillers who do not take care of CST, so I call them gum turpentine distillers. And as you see, our material can go either way, either to the CST distiller or the gum turpentine distiller. Now let's take a look at the market. Crude sulfate turpentine, I mean, we see the numbers that Michel is giving us. Thank you very much, Michel. 200,000 tons or so per crude ton of CST, some 150,000 tons of gum turpentine, mainly China, but also Brazil. China absorbs the material itself, more or less, then of course Brazil and others. So let's say 150 and 200. So if I compare those three routes, you see sulfur, CST, continues at everything, but sulfur components, contracts are being done on a 1 to 3 year basis or so. Gum turpentine seasonal, therefore, spot market. And now comes MDF, continuous, no sulfur, diversification and local sourcing. I'll give you some business cases later on and we'll show you. There will be local sourcing possible. If you ship a container, an isotainer with turpentine from Europe to India, then that would mean you would spend some $200 or so, plus minus, just an order of magnitude. You'll also ship some carbon footprint with it. That is not good for the product if it's a consumer product. And on top, in our case, it's a good story because we put something bad into a bottle and selling it. So that's quite a nice story. So in the end, MDF turpentine combines all the advantages of all those processes. Now, how much is it? The next slide will give you first of all, a theoretical overview. The total amount of medium density fiberboard produced uses some 112 million tons of 112 million cubic meters. That boils down to around 92 million tons of wood dry matter. That's a bit less than pulp and paper, but it's quite a number, obviously. If all those MDF factories would use pine tree, which is not the case, and would use 3 kilograms per ton of dry matter of turpentine, which is the number that the pulp mills also find, only that they relate it to the final pulp and consider that the pulp takes only the 70% cellulose and hemicellulose out of the fiber. We take the whole fiber, therefore the numbers differ by a factor of 0.7. Other than that, around 3%. You also got to consider, and then I go to the next slide, some 50% use pine. Then there's spruce and fir, because softwood is essential, because hardwood gives bad mechanical properties. And some also use acacia, rubber tree, and eucalyptus. But in the order of magnitude, 50% use pine. So here's the numbers. In Europe, there is around 20,000, that's the second row, 20 million tons of wood being used, giving a theoretical value of 58,000 tons. 50% of that would be like 30. In Asia, one must say the 65 million cubic meters are nameplate capacity. It is not really known how much is produced there or how good they are in operation. Anyway, the number, the theoretical number, therefore, would be 180, and then half of that would be 90. Australia and New Zealand, there are 6 plants that I'll show you, giving a potential of like 3,000 tons. And then we have North America, 12 factories in the United States, 5 in Canada, 5 in Mexico, giving this amount that you see there. And then there is 8 million cubic meters or 6.5 million tons of wood in Brazil. And as you know, they use, for example, the Pinus Ellioti, of course. There's one plantation that lies in a MDF factory lies in the middle of a Pinus Ellioti plantation. That's, of course, very exciting. Other trees as well. So that gives these numbers, and now the question is how good is the material and what is the business case for an MDF factory? The next table, you might think, oh my God, I can't read this table. You shouldn't, because it's just an action painting. What I want to tell you there is we are compiling data from all over the world, considering different pine species, with their alpha-beta content as well as the yield in kilograms turpentine per ton dry matter. In my lab, my co-workers, now comes my other function, my co-workers are permanently doing steam distillation to analyze wood samples, steam distillation for the yield, and then GCMS, of course, to determine the alpha-beta content. So this table is constantly filling, and please feel free to share information if you have or want to with me. On that basis, I was calculating, of course, or compiling the yield, and then I defined a quality factor, and the quality factor is nothing else than the alpha plus beta content divided by the alpha and beta content for Pinus Ellioti, which is around 0.9, giving a quality factor. And with that, I analyzed some business cases. The business cases are the following. I'm looking at our plant in Barwood, 500,000 cubic meters. Now, so long as a market, it's a single typical MDF plant. So 500 is a Barwood. Brazil, the one I mentioned, with the Pinus Ellioti, 600,000 cubic meters. Then there is the US, but unfortunately only one with Pinus palustris. There is Australia, Pinus radiata, with a wonderful beta content, of course. And then we have Portugal, Spain, maritime pine, Pinus pinasta, and then Turkey with also Pinus sylvestris. However, the alpha-beta content is higher because the tree reacts differently in that climate, and their plants are quite big. It's a totally different market. With that, I calculated the amounts. As you can see, alpha pinene, beta pinene, AB content, the quality factor, and then the yield in kilograms per ton dry matter. Let's take a quick look at those factories. You see here, South America on top, Brazil in the south. I mean, you know all those locations and where they have the pulp mills and the timber factories and the tree tapping. This is also where the MDF factories are located. Down you see the US, especially in the southwest, you see all the MDF factories for a good reason, of course. And if you look at Pinus palustris, this is their typical habitat in the US southwest. So we have the MDF factory, pulp and paper, and of course, many of your companies are located down there in the southeast of the United States. Here you see Australia, sorry, it's a bit small, 3 plants, MDF plants on the east coast, New Zealand also 3, and they use Pinus radiata, typical plant size 300,000 cubic meters, and there is a turpentine distiller in New Zealand, of course, and the gentleman working there is also here, of course. I was also talking to Lou, who is involved there. In Portugal and Spain, 9 factories, Pinus pinasta, 9 MDF factories, and we all know there's one big distiller in that area, and then a bit up north, and there's 2 distillers a bit down south from there. And so again, we talk about local procurement and some very interesting material. This curve you can download and at the Brazilian export statistics. It's open. So I did, and the last numbers from August show the gum turpentine price of Pinus Ellioti from Brazil, free on board. And the last number is obviously under, that's the August number I just inserted, that's under $2,000 per ton. My subject is not business at that point, or at least not numbers. However, I wanted to give you an order of magnitude to have an idea about what the business case could be. So I took the 13-year average, which in this case is $2,300 per ton. It's a hypothetical value, of course. I know the price is down at the moment, but it will give you a fairly good indication of how a business could look like. And again, it's hypothetical. I took that number and as you saw before, I have the quality factor. So I just multiplied. And here's the result. I transferred dollars into euros, so 2,150 euro per ton. Hypothetical again, and please note, no business information, only meant to assess an order of magnitude. Of course, we know that it's not that bad at all. And now you see the business cases, and in this rows you'll see the turpentine in euro per ton. Obviously, Pinus Elioti as a reference case will be the 2,150 euro. The estimated revenue that comes from the mass balance for the turpentine plant, and euro per cubic meter. I'll come back later to that one. So you see, in Bauer, it's not really, in that hypothetical case, of course, not that interesting. Brazil, 5 million, that's already a nice number. US with Pinus palustris, this single plant is rather an exception, I must say. Australia, smaller plants, but very nice material, of course, giving a high price, but not that high yield. And Spain, also not too bad at all, 2.5 million. And Turkey, due to the big plant size, also quite a nice number. Let me state one more time, most of those values are theoretical values or literature values, because I have not analyzed the very wood that is going in there. In case number one, yes, permanently, and the other cases not, so that also always has to be double-checked by steam distillation or analysis of the wood that you use there. So those are literature values, but I think from what I saw, they're quite good, actually. The last row is not really of interest to you, euros per cubic meters. That's how the MDF people calculate. So euros per cubic meters, what does it say? Let me give you a reference. The sales price for MDF at the moment is low and capacities are down, so that's the same story. 300 to 350 euro per cubic meters. So now that number becomes a value. So that means the 3 in the first row is like 1% of the revenue. The sales price. Let's assume they have a 10% profit on their sales. Assume, it's just an assumption, please. Then the profit would be 30 million. So 3 out of 30 would be 10% of the profit. Not too bad at all. You go to Brazil, 9 or so. That turpentine sale would be 30%. You would increase your profit by 30%. That's quite a motivation, obviously, for an MDF factory to produce turpentine from MDF. That would probably, obviously, be quite some motivation. But again, these are theoretical numbers. And of course, you see the others. I don't see it. I have to look here. Spain, 8.2, also quite a nice number. And Turkey, also not too bad at all. But Turkey is, of course, nice because they have these big plants. The timeline for the project, how does it look like? The emission thing can be done within a couple of months, no problem at all. If you have a problem, or the industry has a problem, within a couple of months it can be solved. And that is not really a problem. It's very quick once you know where to tap the plant. For MDF turpentine, the installation goes within around 1 year, depending, of course, at the moment, automation equipment is a long lead equipment, rather funny, but this is also getting much better. We do a process design package for giving you the process engineering information, and with that you can go either to a CST recovery contractor or any decent engineering company that's going to build it for you. It's not really that complicated once you know where to go. We provide 2 sizes. We do it modular. You saw 300, 600, that's around the order of magnitude. 2 sizes design, and there are 3 options for heat recovery. And there are enough heat sinks to get rid of the heat for condensing. So that's why it is neutral. And that's the turpentine recovery thing. We developed the market by selling licenses on the market. First of all, for the VOC reduction thing, because obviously there's a high pressure and quite an interest in the market there. That's why we started there. We start now with the turpentine recovery. Since our reference plant, our first one, starts next year summer, our summer, July, It's obvious that nobody else will do it before that, but after. And we are currently exploring different licensing and cooperation models. And I've been talking to quite a few of you, and that's why I'm also very happy to be here today. Let me shortly summarize and come up with some conclusions. So there's a new route to the Turpentine. Nobody else has done it before to tap an MDF plant in that order of magnitude. We solve environmental problems, and at the same time, we create revenue for the MDF producers. The worldwide production potential is over 100,000 tons per year, which is a remarkable number, obviously. The yield and the composition depends, of course, on the tree and species you're using, so that's crucial to select the right plant with the right raw material, that's obvious. And yeah, we have found a completely new business in the pine chemicals industry and have started that. You will find the references at the last slide, and I thank you very much for your attention. Thank you.